And then what else? Y plus 6 over 6 to be the sine. Now, I'm not done because I want to say what is x going to equal, what is y going to equal, but I think I need it like that because now cos squared plus sine squared would equal 1. So therefore, x would be 6 cos t plus 2. Y would be 6 sine t minus 6. And that would be the best parameterization for this particular shape. The parameterization for a circle and an ellipse look very, very similar. But there is one difference, right? Coefficients. Okay? The coefficients would not be the same. So far, so good? All right. Yeah.
And just to verify, you said to, just in general, always make x go with cosine and y go with sine.
If it's a conic.
Okay.
If it's conic. If I had the parabola we did a moment ago, y equal x squared, there's no advantage to doing sines and cosines there. That wouldn't make any sense from that standpoint. But in this situation here, circles, ellipses, the reason I need cosine is I need that cos squared plus sine squared equals 1 property in order to make the equation work. Because I can't write it as a function like I can with a parabola. Now, how about a hyperbola? I want to parameterize, and I'm gonna keep this one easy. I'm gonna center it at the origin. Will sine and cosine work? Why not? It worked for the ellipse and the circle. Because I was adding them. Cos squared plus sine squared equals 1, but cos squared minus sine squared, or vice versa. Can you think of any conic sections? Excuse me, not conic sections, any trig functions where the difference of squares is 1? Secant and tangent. So which difference do I want? Or secant squared minus tan squared. Do you all agree with that? Secant squared minus tan squared is in fact equal to 1. So if I make this whole thing be the secant squared of t and I make this whole thing be the tangent squared of t, would that work? Yes. Is it the only one that would work? Or is there one with cosecant and cotangent?
Unfortunately.
Yes, and you would just wave at it as it passes by, right? You're not even tempted to go there, am I right?
Correct.
Remember, we're going to be doing things like arc length next day, which involves taking derivatives. You don't want to do cosecant cotangent. You can, and you will be correct, but it is a lot of pain and suffering involved. I'll just leave it at that. Those are not our favorite functions. Okay, so what do I want to say? Let x equal, let y equal, I wrote it over here. What do I want x to equal?
X over 8 squared.
I want the whole thing to be secant squared.
Yeah. So 8 cosine of t, or 8 secant.
How about 8 secant? Yeah, that would be a better choice. And let y be,
4, 10, see.
if I do this, then that will work. Because secant squared minus tan squared. Real quick check, if I divide by 8, I divide by 4, I square them, I get, yep, life is good. So I said x for cosine, y for sine, if it's a conic where you're going to be doing a sum of squares, so ellipse, circle. If you're going to be doing a hyperbola where it's a difference of squares, you can't use sine and cosine, that won't work, but secant and tangent would work. And these, turn out, these are going to be very, very common things that we do over time. Okay? So far, so good? Now, I have a favorite shape. This is one we're going to analyze in many, many ways. We're going to look at derivatives, we're going to look at arc length, heck, we're even going to look at area. Hmm. Well, we could make a table of values. We could start that way. We could go like this. We just said a moment ago. So let's do the easy one. 0, pi over 2, pi, 3 pi over 2, back to 2 pi. All right, so when t is 0, cosine of 0 is 1, so cos cubed is 1. Sine of 0 is 0, so sine cubed is 0. Okay, good. If I'm at pi over 2, the cosine is 0 and the sine is 1, and I'm cubing them both. Okay. If I'm at pi, the cosine is -1 and I'm cubing it, the sine is 0. At 3 pi over 2, the cosine is 0, but the sine is -1 and I'm cubing it. And at 2 pi, I'm back to the beginning. Okay, good. Well, that makes it easy. I pass through 1, 0. I pass through 0, 1. I pass through -1, 0. And I pass through 0, -1. So you guys all know what this looks like, right?
Sure.
Now we just have to fill in some of the other values of t. That's all. That's all we got to do. Okay, how about we do something like, I don't know, we could pick pi over 4. Right? We could do something like that. The cosine would be root 2 over 2, and so would the sine. Oh, okay, so my coordinates would be root 2 over 2 cubed, comma, root 2 over 2 cubed. But give me a decimal for root 2 over 2 cubed. Because I just want to plot the point. Just cube root 2 over, well, root 2 over 2 squared is a half. So the answer is just going to be root 2 over 4, isn't it? And what's root 2 over 4? It's about how big? 0.35. So maybe about there. Oh, I think it's not a circle. It caved in, kind of. So that's really not helpful, huh? Well, I do have those 4 points, and like I said, this is my favorite shape to work with. We're going to study this one over the next few days. This is not a bad idea, but it's not enough. I got sines and cosines. Can't I somehow use that to my advantage? Yeah, but I got cubes though. How would I do that? Oh, let me ask you a question. True or false? Is it always true or is it not always true? You have quantity that's equal and you raise them both to the same power, is it still equal? Yeah. It's not necessarily true if I said things like roots and stuff, because you have to worry about plus or minuses, but that would be true. Then suggests we raise both sides to the 2/3 power, which is kind of weird. X to the 2/3 equals cos squared t. Y to the 2/3 equals sine squared t. So what does that mean then? I have x to the 2/3 plus y to the 2/3 equals 1. Huh. Now, am I still going to get those 4 points, the zeros and ones? Will that still work? Yeah, because I'm squaring the -1 now, and yeah, that will still work. And it turns out, like I said, we're going to study this one because it has such cool properties. I like to call it my ninja throwing star. Now, why this one is incredibly cool, it's defined everywhere, but it's not differentiable everywhere. It is continuous everywhere. You gotta be careful because it's really sharp. Why? Because these are approaching vertical from both sides. What do we call that kind of point? Do you remember? It's something you did in Calc 1, graphing. No, it's not an asymptote because I don't have no dotted lines there. It's called a cusp. Remember those things? Cusps. Cusps are non-differentiable points. In fact, let me remind you of a cusp that you hopefully did in Calc 1. It's a simple one. If I want to do the graph of y equals x to the 2/3. It's defined everywhere. but it's not differentiable at the origin. The reason is, when I take the derivative of that, it's going to throw an x in the denominator, so the derivative does not exist at 0, but the function does. And the derivative from this direction is approaching positive infinity, the derivative from this direction is approaching negative infinity. It's cool. So do you remember doing graphs in Calc 1 with cusps? Right? You had different things. A cusp is a non-differentiable point. I'm continuous there, I'm defined there, but I can't take the derivative. Now, would this also be a cusp? It's going sideways. I'm approaching horizontal, It turns out it's also a cusp. And so what we're going to learn next day is how to do the derivatives of this. Will I get any vertical tangent lines? Yeah. Right here. Will I get any horizontal tangent lines? Right here, because it approaches it. So it's some crazy weirdness is going on in this shape. Based on what we did just a moment ago when I said consider pi over 4 and you cubed, right? You got this little dippity-doo point there. Well, you know you were going to get 4 of these now, right? You might have been able to kind of reverse engineer this and say, well, you know, I got to get to there, I got to get to there. And more or less, this almost has to be computer generated. But computers will have a difficult time often because it's not a function. Remember, when you ask your calculator to graph, it wants functional input. If I wanted to graph a circle, how do we graph a circle on a calculator? Remember, there's a really simple rule. Can't graph the circle, but you can graph top half, bottom half. You just enter 2. Oh, so could I maybe just do one of these pieces? Or even the top 2 pieces? And then just do, yes. So if I asked you to solve for y, that's what I want to do next. Because I'm going to show you next day. We're going to do the derivatives using the rules we're going to develop for parametric equations. But it turns out I actually can take the derivative of this, okay? If I solve for y and I only consider top half or bottom half as separate entities. I'm going to show you where you actually have done this in the past. So if I do this, I don't want to do it from there, I want to do it from here. Because if I do it from here, I don't want my inverse something of another trig function. It's too creepy. So is this true? Yes, no, maybe? Yeah. So how would I differentiate this? I can solve for y, but there's a better way. What would it be? Starts with an I. Implicit, oh yeah. But actually implicit would be much easier than solving for y. If I try to solve for y, I can do this. This isn't the worst thing you've ever seen, but it is kind of ugly. Implicit might be easier, but we can do this. But I think it's easier if you think of this as top half, bottom half. And then either do it directly or do it implicitly. And then you can tell me what the derivative is at every single point, because the plus or minus, you have the top half, you have the bottom half. When you're first introduced to implicit differentiation, and this will be a lecture I do in a Calc 3 class when we get to the Calc 3 version of implicit. So if we consider a circle of radius r, pick any point on the circle, I'd like the slope of the tangent line. That's a totally reasonable question. The slope of a tangent line. Well, pre-implicit differentiation, what you did, and this is, by the way, this is exactly the segue into what we're going to do next day. Because if I'm working with a shape that is not a function and I'm talking about derivatives, that's what implicit differentiation did for us. But sometimes we would like the answer to be a little cleaner. So we said, let's consider top half and bottom half. So the top half was y equals the positive square root. The bottom half was y equals the negative square root, right? And so then we said, just straight off, let's differentiate. So we got 1/2 r squared minus x squared to the negative 1/2 times negative 2x. The 2's would cancel, and that gives us negative x over the square root. And I'll put it back in like that, which is just simply negative negative x over y. How about over here? dy dx equals this is correct. This is probably more useful though, right? Easier to work with. So over here I'd have negative 1/2 r squared minus x squared to the negative 1/2 times negative 2x. 2's would cancel, and I would have negative 2x on top, and on the bottom, I'm sorry, negative x on top, and on the bottom I'd have negative the square root of r squared minus x squared, which is equal to negative x over y again. So if I did top half, bottom half as separate entities completely, I got the same answer, didn't I? In both cases, I got negative x over y. But wait a minute, but this has got 2 negatives and that's got 1. Yeah, because that's still the same thing. Now, if I'd done it implicitly, which is actually the most efficient way, I wouldn't have had to rearrange at all. I just differentiate both sides. Okay, so when you see a y, you don't see a y, you see function, remember. So this would be 2x plus 2y times the derivative of y. And the derivative of r squared would be 0. That's just a number. So when I gather terms, this is actually considerably faster, isn't it? But what we're going to do is going to be more akin to the first one in that I want to be able to get the x's and y's manipulated, but through the use of the parameter. Now, I'm speaking vaguely on purpose because that's like the first half of the lecture is just derivatives. But it's going to be actually a fairly simple thing because when I differentiate, I'm only differentiating with respect to one independent variable, but that will always be the t. So the answer to my derivative might not look x and y-ish. But what did we just do? We took something x and y-ish, converted it to something t-ish, we took something t-ish, converted it to x and y. We're going to do the same thing with derivatives. We're going to use the parametric form, differentiate that, but then we can change that answer back to x and y, in other words. Does that make sense? So what I'm going to do is go back to this, and I'm going to describe x as being r cos t, y being r sin t, and then we're going to differentiate it that way. And in the very end, we're still going to get negative x over y as a result. Even though we had t's, we'll be able to substitute back. And it's kind of cool because you're going to see this nice way of going back and forth. And you sort of choose your path, whichever seems like the path of least resistance, depending on what you're being asked. Because otherwise, something like doing a derivative here, I can differentiate both sides implicitly, or I can differentiate this way, which looks more like this version. Okay, I want to be able to do both, and then we're going to look at it parametrically.
How did, maybe I got lost somewhere. How did both of them end up as negative x over y when the bottom has 2 negatives?
Oh, no. That's why.
Oh, it's a negative.
Well, no, I left the negative on top because this is y. And over here, this is y. Remember, we did top half and bottom half. They're 2 different functions.
Right.
One's a root, the other's the negative of the root. So in my final answer to the derivative, my denominator is the negative of the root, which is y. Exactly. They're 2 different functions. I can't get the same actual quotients for both. That would be impossible. I got 2 different quotients, but in both cases I got negative x over whatever y was. That's always going to work that way. Would it work that way if you were doing an ellipse or a hyperbola? Yeah, it wouldn't be as clean. It'd be kind of ugly. Okay, any question on this? Okay, I think we're at a good spot.